Macros let us do metaprogramming in Rust. Metaprogramming allows us to treat our code as data, manipulate it, expand it, and generate new code. Macros let us do a lot of things, but I've broken this video down into 3 parts. We'll go over the basics of how you can use macro rules to make your own macros. I'll show a somewhat real-life use case that I've been working with lately, and we'll implement another programming language within Rust to demonstrate how you can create domain-specific languages, DSLs. This series is accompanied by a free book. Check the description for links straight to this chapter. My name is Daniel. Welcome to Iris. There are 2 types of macro in Rust: macro rules, also known as declarative macros or macros by example, and proc macros. We won't be dealing with proc macros in this series, but they allow you to create custom derived macros and custom attributes. They also let you make the same function style macros that we'll be making with macro rules, but they can unlock even more power. If you'd like me to do a video on this after the Iris series, let me know in the comments. Today though, we're just covering macro rules. Macro rules is itself a macro, providing its own domain-specific language that allows you to create more macros. This gets very powerful and, honestly, a bit weird. Let's take it slow. The general layout of macro rules looks like this. We write macro rules with an exclamation mark followed by the name of the macro that we're creating. We then have a block containing a list of rules. The rule contains a pattern to match on, which itself potentially contains metavariables, which we'll discuss later. Each rule also has a block that describes how code will be generated when the macro is invoked with a matching pattern. Rather than macro rules generating code with a simple copy-paste, it works on the abstract syntax tree, or AST. This is an intermediate step of the compilation process where your code has already been turned into data structures that help the compiler understand what your program does. This makes it much safer and more fully featured than copy-paste style macros that you might have used in the past. We'll start by making a hello world macro that produces a string. As we said a moment ago, immediately after macro rules, we provide the name of the macro we're creating, in this case, hello. Our first draft won't match anything between the brackets, so we're going to leave those empty. We then have an arrow followed by some curly brackets surrounding what our macro will generate. Here's a little test to make sure it works and to show how it might be used. Our hello macro simply creates a string containing hello world at the site where the macro is called, in this case inside an assert EQ macro. This type of macro could be useful if you have a block of code you need to repeat but don't want to put in a function, but let's be honest, that's not going to come up very often. Let's upgrade our macro to match a pattern. What madness is this? What kind of parameters are we passing to this macro? The key to understanding the power of macros is that they don't take parameters. The thing in the brackets at the start of each rule is a pattern, and that pattern can be almost anything. The content of the macro's invocation is broken up into something called a token tree, which we'll talk about in the next section. Here, this must be present is passed as 4 token trees, this must be, and present. Different tokens won't match our pattern though, so this won't compile. But we can invoke different rules based on the match pattern. So we could match several people by making a rule for each of them, but we obviously can't write out every possible thing that we might want to match on. What if we want to be able to say hello to lots of different people? Instead, we can capture tokens into metavariables. Things got a little bit weird here, right? Let's step through our changes. First, we added a metavariable, and you'll immediately notice this looks nothing like a normal function parameter in Rust. In macro rules, we can parameterize tokens into metavariables which are preceded by a $, followed by a colon, and what's called a fragment specifier. Fragment specifiers are a bit like types, but are specific to how Rust classifies token trees. We can't specify str here, but we can specify that we expect a literal, which is any raw value. That includes string slices, but could also be numbers and booleans and other things as well. You might still wonder what happens if our macro gets a literal that's not a str, and the answer is it won't compile. The person who passed in the non-struct will get an error message relating to the push struct method on string, but admittedly, errors on macros like this can just be a little harder to work with. That said, over the 10 years since Rust came out, contributors to the language have and continue to do a lot of work to clarify errors across the board. Anyway, there are a number of different fragment specifiers, some of which overlap with each other. We'll go over them more in the next section. The second change we've made here is that inside of the code block, we've added another code block. The reason for this is that when we invoke the macro, Rust generates code at the point where you place the macro. If we didn't have the extra brackets, when we use the macro in our assert EQ, our code would look to Rust as if it were this. This doesn't work because assert EQ, which is also a macro, expects to match expressions represented by the fragment specifier expr. Oh. I had to work out how to vocalize a few unique things this time. Wish me luck. In Rust, an expression is a segment of code that produces a value. So, string from hello is an expression, but let mute output equals string from hello is not. That's a statement. A statement. Blocks of code, even multiple statements surrounded by curly brackets, are expressions though. They have a value, even if the value is the unit type. When we wrap our generated code in curly brackets then and have some value as the final line, our code block becomes a single expression, the value and type of which matches the final value. This means that when we add those curly brackets to our macro, the generated code now looks like this, which is valid. Expressions in Rust are particularly useful as they have a type and a value just like variables, allowing you to use them inside other expressions. Let's go deeper and add another rule. Let's bring back our original behavior for an empty hello macro. This is fine, but we're repeating ourselves a bit. We should avoid having two copies of the hello string slice. To maintain consistency, we could call our macro recursively, like this. We're nearly there now, but I think our hello macro is missing one critical feature. What if I want to greet lots of people at the same time? We can repeat patterns inside macros by surrounding them with parentheses, preceded by a dollar and followed by either a question, a plus, or a star. Question means the content is repeated 0 or 1 times, plus means 1 or more times, and star means 0 or more times. You can add a separator to the repeat pattern by placing it before the repeat character. This token can be almost anything except the repeat tokens or delimiter tokens. The most common separators you're likely to use are commas or semicolons, but you could use something like tildes, you know, if you're twisted. Repeats are used in rule matchers to match patterns, including metavariables, multiple times. They're also used in code generation to repeat code for each repeated metavariable. We already have 0 and 1 metavariables dealt with, so we want a rule in our macro that takes 2 or more inputs. For want of space, I'm going to condense the formatting from now on, so keep an eye out for those double curly brackets. Our new rule looks a bit like the previous one, but now there's a comma after name literal, and then a repeat pattern. The repeat pattern contains its own metavariable, rest literal, which will be used to store all metavariables passed to the macro after the first. It uses a plus to show that there must be at least one additional metavariable, but there may be many. In the body of the macro, we initialize our output in much the same way as we do in the version with no inputs, by calling the hello macro with just the first metavariable. We then have another repeat pattern that contains code with the rest metavariable. Because we have a repeated metavariable inside a repeated block, this block will be repeated for every literal that rest matched to. If we were to expand the code generated for the final test, it would look something like this. Hopefully you're starting to see why writing a quick macro can really cut down on repeated boilerplate code. We're really only making a quick toy macro too to demonstrate the power that they provide. Now you might be wondering if we can use repeats to reduce the number of match arms that we have. We unfortunately can't do things like treat the first and last element of repeats differently using macro repeats. But we can merge the second and third arms using a star. You'll notice that the comma after name literal has moved inside the repeat pattern, and the comma being used as a separator for the repeat pattern has been dropped. This is because if we kept the comma outside the repeat, hello Yuki would have to be hello Yuki comma to work. Instead, we've moved the comma token to the beginning of the repeat pattern, which can contain things that aren't metavariables too. Okay, so I wasn't exactly lying when I said that we couldn't treat the first and last elements differently with macro repeats. We can't do it with just macro repeats. We can work around it with low-cost language features like slices. We can split the names out directly into an array. This will be part of the binary created at compile time, so it doesn't require any heap allocations. Next, let's get an iterator over the array. By precisely specifying the type of the iterator here, we can avoid Rust not knowing what type to infer if the iterator is empty. We'll initialize our string as before. If no metavariables were passed, then the array will be empty, so we'll use our default value, otherwise we'll take the first item. Then we'll loop until no more items are in the iterator. By looking ahead to see if there are more items, we can now use grammatically correct separators between our names, and we'll add an exclamation mark for funsies. Finally, we do need to update our tests for the improved grammar. Being able to quickly compose macros like this can save us a lot of time when repeating the same code over and over. Rust, like most languages, turns your human-written code into tokens that it can process. Groups of tokens can form a token tree. If tokens are protons and neutrons, then token trees are atoms, and they're the smallest thing that we can process in macro rules. An important differentiation with token trees to a simple list of tokens are that delimiters, that's parenthesis, square brackets, and curly brackets, are all matched up for us. For example, if we break the statement let hello equals string from hello into tokens, it looks like this. But if we break it into token trees, then the parenthesis is a single token tree that contains the token tree hello. In the previous hello example, we captured token trees that were literals into metavariables with fragment specifiers, but we can categorize token trees as more than just literals in macro rules. Here's a quick rundown of some of the most common fragment specifiers. TT matches a token tree, which is any single token other than delimiters. Remember when we wrote this must be present in our silly example earlier? Each word is a token tree. We'll go over breaking up delimited token trees a bit later. Literal is the specifier we already used to match against a literal value. This matches against integers, floats, booleans, characters, and a whole set of string types, including string literals, raw string literals, byte string literals, C string literals, and so on. Expr is short for expression. An expression is any token tree that has a value. For example, string from hello is an expression, but let hello equals string from hello is not. Block is specifically a block expression. Like the code we were generating in our hello example, blocks can have multiple statements surrounded by curly brackets to make it a block expression. Of course, all block expressions are also expressions, so you may not end up using this fragment specifier too often. Stummet is short for statement. This is a line of code or an item. For example, let hello equals string from hello is a statement, but so are items like modules, structs, and functions. Ident is short for identifier. These are things like variable names, type names, or any word that's not specifically a keyword. That said, you can make a raw identifier using rhash, so while true is not an identifier because it's a keyword, rhash_true is an identifier. You're most likely to see raw identifiers in macros, particularly ones that are for domain-specific languages. For example, DSLs that are used to create HTML might want to let you use the type keyword as it's an HTML attribute, so you might see rhash_type to make it a raw identifier. In our earlier example, each word in this must be present is an identifier. Identifiers don't need to already exist in code. Path is a type path. This could be an identifier on its own or a sequence of identifiers separated by two colon tokens. Like with identifiers, they don't need to exist within the code, they just need to fit the pattern. Tie is short for type. This could be a type or a type description. For example, dime clone plus send is what's called a parenthesized type, though traits like clone and send are also types on their own, as are structs like string. Item is anything that could belong to a crate, such as functions, modules, static items, use statements, etc. Viz, short for visibility, describes the visibility of something else. For example, pub, pub crate, or pub super. Lifetime matches explicit lifetime annotations such as a or static, each of which start with a single apostrophe character. Meta's a weird one. It matches attributes. It could be useful if you want to construct a type and pass in attributes to apply to it. There's a lot here, and I've ignored backwards compatible fragment specifiers. Some fragment specifiers have changed behavior over the years. If you want to see a full list of fragment specifiers or more complete descriptions of each of them, don't forget to check out the official documentation, link in the description. The example we ran through earlier to build up our understanding of how macros work was very abstract and not very useful, so I wanted to go over how I've started using macros. Now, I'm going to show you how I'm using macros in my code, but for the purposes of Iris, I've modified the examples to avoid using crates. Crates are how we share reusable Rust code between each other, but if you haven't noticed, I've avoided using any in the series to focus purely on the core of the language. If you're comfortable with crates and async Rust already, and you're curious what the differences are in my real code, there's a link to the app I've been building on stream in the description of this video. In the job tracker app I've been building with the help of folks on my streams, I've leaned heavily into composing the types using traits to form common behaviors. For example, at the time of filming this video, I allowed the user to create things like flags, roles, and values that belong to companies, so those types implement the trait hasCompany. Here's an example of how that might look for role. Role is pretty simple. It has an ID of its own, an ID that links it to a company, and a name. The hasCompany trait has a single method, getCompanyID. When we implement it for role, it just returns that company ID, which is copy, so the code is nice and simple. I'm also a huge advocate for unit testing, and even for code like this, we ought to provide a simple unit test. This is pretty nice code, even if I do say so myself. It's clean, easy to understand, and easy to use. But is it dry? Dry in this context stands for don't repeat yourself. Every time we add a new storable item, we'll have to implement the trait and write the test for its implementation. This isn't the only trait that's applied to storable types, and we have multiple storage types that also have lots of shared traits that all need implementing and testing. Let's look at how macros can help us generate boilerplate code. First, we'll create a macro that will implement hasCompany for any type that has a company ID field. Obviously, if you try to implement this trait on something without this field, the macro will generate code that won't compile. But if you need to do that, you can still write your own implementation. Role, flag, and value all have this field though, so now we can implement the trait with one short line each. Replacing the test is a little harder though. We can't easily write a generic test that will work for role and flag and value, as these types are instantiated in different ways. What we need to do is have a consistent way to create test instances of the thing being tested. To do this, I created a test helper that can be applied to almost any type. Its only job is to return an instantiated value of that type. This trait exists in a central location, and each test macro sits alongside the trait it creates tests for. We can create the test by taking two metavariables separated by a comma token. Test name is an ident which will be used to create the name of the test function. Storable is what I call any object in this project that can be stored, and in this case is the test subject. The test here is super rudimentary. We're just going to make sure that when we request the ID, we get something back. By implementing the trait for each type that I want to test, I can add tests trivially like this. This might initially seem like it was just as much work as before, but as we add more traits and more types that implement those traits, the amount of extra work drops dramatically. Furthermore, there are more complex examples in Theo's job tracker, like the ones that manage the storing and recalling of these storable objects. Have you ever wanted to write your own programming language? We're going to get a little bit silly shortly, but domain-specific languages, DSLs, can be incredibly useful for conceptualizing your code in ways meaningful to your domain. For example, JSX is a DSL for writing React in JavaScript. If you're a web developer ultimately creating HTML, which of these is more readable? This, which is valid JavaScript, or this, which is not valid JavaScript? I think it's undeniably easier to understand the one that looks more like HTML. The React DSL gets converted back to JavaScript to be run in a JavaScript runtime. So I promised silly, let's write our own DSL, a brain fudge transpiler. A transpiler takes one language and turns it into another, like how React DSL is transpiled into JavaScript. The programming language brain fudge was created by Urban Müller in 1993. The language is what's known as an esoteric language, which is, loosely speaking, a fully functioning language that you would never actually want to use. Often they're considered jokes, and brain fudge certainly is that, but it actually lets us write real programs with just 8 instructions. This makes it ideal for demonstrating how to make a full language inside of Rust. Brain fudge operates on a theoretically infinite sequence of memory initialized to 0. You start with a pointer pointing at the first cell in memory, and then process instructions that allow you to move the pointer, modify the data at that point in memory, perform loops, and either output or input data at the current pointer location. We do all of this with the following 8 instructions. Greater than increments the pointer position, moving it to the next position in memory. Less than decrements the pointer position, moving it to the previous position in memory. Add increments the value at the current position in memory. Minus decrements the value at the current position in memory. Period outputs the value that's currently stored at that position in memory. Comma takes some input and stores it in the current position in memory, though we are going to ignore comma for this video. Square brackets loop the contained code. Each time the loop begins, the value at the current position is checked. If the value is 0, it skips the loop. That sounds easy enough, right? Well, here's Hello World in brain fudge. Don't panic, we're not here to learn brain fudge ourselves. We're just going to trust that this is the Hello World program, we'll implement the instructions and see what happens when we run it. We're going to use 2 macros. First, let's create a macro that initializes our program. The input to our transpiler is a repeat pattern of token tree, which we'll store in the metavariable token. As it happens, the individual characters that make up brain fudge are all tokens in Rust as well, so this should work out. Memory is going to be our program's memory. We're using a vec with a single initialized value of 0 under the assumption that even the smallest program requires 1 word of memory, and we can't have an infinite vec, so we'll expand it as necessary. Brain fudge doesn't specify a word size, so we're going to use 8 bits. You can use larger words if you like, but different programs might function differently depending on what word size is used and how overflows are handled. More on that later. Constantly expanding the vec isn't very efficient. We'll be doing a lot of heap reallocations, but are we taking this seriously? No, not at all. Pointer points to the current position in memory, or as we'll be using it, it's the index into our vector. Output is where we'll store output data from the program. At the end of the macro, we take the output vec of U8 and collect it to a string by naively considering each byte to be an ASCII character. Again, depending on how you want to work with your programs, you may want to process the data differently, but this is fine for us. Now, while this is the official Hello World, and actually that's kind of hard to read, let's add some white space. Yeah, no, that did not help. Anyway, while this is Hello World, so is this. In the official Hello World, loops are used to increment values, but in this version, we're just adding to the current memory location, exporting it, and moving to the next memory location. Let's turn this into a test. I made this version of Hello World because it only uses 3 characters out of the 8 used in brain fudge, so to make this test pass, we only need to implement those 3 operations. So now we have a test, let's work out how to handle greater than, add, and period. We'll create a new helper macro that can handle each of these tokens by having a rule that matches each specific token. These rules will be called recursively, so there'll also need to be a special rule to handle where there are no tokens left so that we have an endpoint to the recursion. To make it work, each rule will need access to the memory, the pointer, and the output buffer, so we'll add an expectation of those to the match pattern. Additionally, because each rule only handles 1 instruction, we need to pass the rest of the instructions to the macro again recursively. Unlike our earlier examples, we're going to use a semicolon as a separator in our pattern matching. The reason for this is because brain fudge uses commas as part of its syntax, but not because it impacts our ability to parse brain fudge code. Even if the first token in a program is a comma, it still comes after the last separator we match against. What we're doing here is improving readability for anyone using the macro. Let's handle plus tokens. All we need to do is add 1 to the value in memory at the pointer. Brain fudge is non-specific about what to do in the event of an overflow, so I'm going to choose to allow it to wrap around. Next, let's implement the rule for the greater than token. In this case, we're incrementing the value of the pointer, but this time I don't want to wrap. We're using saturating add for the specific reason we want to be consistent, and I don't want to wrap a usize on subtract. You'll see why later. We also need to make sure that anytime we go out of bounds of the memory vec, we resize the vec appropriately and zero the memory. We can do this with a quick loop, pushing zeros onto the end. Next, we want to match the dot operator. It takes the value at the current pointer and writes it to the output buffer. Finally, we have a match arm for when there are no more tokens left that doesn't do anything. Now we can update our brainfudge macro to call the helper passing in the program state. So now we have a program that contains our brainfudge macro, a brainfudge helper macro, and a test. When we build the program, we get this error. Rust keeps track of how many times we recurse, that is, call a functional macro from the same functional macro. By default, the maximum amount of times that we can do this is 128. Our macro, when passing our silly hello world example, recurses 1120 times. So we could avoid recursing by looping through the tokens instead, and that will work for this current instruction set, but it won't work for loops. We probably could come up with a way of mixing loops and recursion, but to keep things simple, we're going to play a dangerous game and manually tell Rust that it's fine for it to recurse 2048 times. The recursion limit attribute applies at the crate level, so be careful with this one. And now our code runs. We've made a great start, we've got almost half the language done already, and I hope that you'll agree this wasn't all that painful. Let's implement some of the other operations. Dealing with less than and minus is easy enough, they're the opposite of what we already have. Minus, similar to add, does a wrapping subtract of the value at the pointer. Less than does a saturating subtract of our pointer. This is where that saturating behavior matters. Were we to wrap a usize of 0 minus 1, it becomes a number so large I can't even say it, let alone build a vector that size. More complex is the loop. Luckily we aren't dealing with individual tokens, we're dealing with token trees. In Rust, certain bracket pairs are considered tokens that wrap other tokens. They're treated as a single token tree that contains more token trees. So Rust will correctly handle them in pairs even when nested. This means to make our loop rule work, we can match against any token tree that starts with an open square bracket, contains more tokens, which may include more square bracket pairs, and matches its ending closed square bracket. This is followed by yet more tokens. How cool is it that we get all of this for free? The loop is really easy to implement too. We check the value at the current pointer position. If it's not 0, we run the code in the loop and check again. If it is 0, then we continue recursing with the rest of the code just like every other rule. To make sure our new code works, we'll update our test with the real hello world. And when we build it, it doesn't work again. It actually gives us a number of errors, all different, all valid, but I'm only showing the first one because it tells us exactly what we need to know. Why is it pointing at 2 greater than signs? We already have a match for greater than, right? Well, here's the problem with using tokens for our DSL. Rust considers 2 greater than symbols to be a single token. Specifically, it's a right shift operator. Tokens in Rust can be multiple characters. Here are our problem tokens and what they mean in each language. Dot dot in Rust is a range literal, but in brainfudge it means output the current value twice. Greater than in Rust is a right shift operator, but in brainfudge it means increment the pointer twice. Less than in Rust is a left shift operator, but in brainfudge it means decrement the pointer twice. Dash greater than in Rust is used when writing function return types. In brainfudge it means decrement the value at the pointer, then increment the pointer. Less than dash in Rust isn't used currently, but it is reserved. In brainfudge, it means decrement the pointer, then decrement the value. So unfortunately, we need to take care of these special cases. Fortunately, while greater than is right shift token, greater than space greater than is 2 greater than tokens. Tokens can be separated by white space, which is ignored by the token tree fragment specifier. All we need to do is split the token and pass it back into the macro. Now when we run the code, it works. So we just created a transpiler for another language inside Rust. That's kind of wild, right? I stopped setting homework, but I thought I'd set a little challenge for anyone who wants to do it. We only implemented 7 of the 8 brainfudge instructions. Can you edit our brainfudge macro to work with programs that take input via the comma token? To do this, I recommend making the following change to the main brainfudge macro. This will allow callers to control inputs and outputs as they please. There is a test in the Iris book that you can copy for a ROT13 program. That's a program that takes each alphabetical letter and shifts it 13 characters. There's no prize for doing this except your own personal growth. If you get stuck or just want to see the answer, it's over in the book, see the description. As ever, thank you so much to my Patreons, as well as the growing community at large. I'm not sure if we'd have made it so far without your support. Next time, in the penultimate video in the Iris series, we're going to look at unsafe Rust and specifically how we keep ourselves, well, safe while using it. If you enjoyed this video, do me a solid and like and subscribe, or if you really want to help me out, let a friend know about me. Don't forget I stream on YouTube on Tuesdays at 7 PM UK time if you're interested in seeing me work on real Rust projects. And whether there or here, I'll see you next time.